Now we'll discuss the four basic data types used in C language. As you can see, I will be using the PDF tutorial cprogramming.pdf. You need to go to page 14 where you'd find this discussed. Also, you may also use the other PDF tutorial essentialc.pdf, and you need to go to page 3 over here. So let me go back to cprogramming.pdf. As I mentioned just now, we'll be discussing the four basic data types. Now, the four basic data types in C are int, char, float, and double. You must keep in mind that there are some derived data types as well, like structures, pointers, etc., which we will be discussing later on. And there is another data type called void, which basically stores nothing. So to understand these data types one by one, we will take the help of our own program, introductory program. So this was our first program. As you can see, this statement, int x comma y. X and y are two variables of type int. That means they are of data type int. When this statement is executed in a C program, what happens is space to store these variables is reserved or allocated in memory. Now, how much space is to be allocated depends on the data type of the variables. Since x and y belong to int data type, therefore 16 bits or 32 bits that amounts to either 2 bytes or 4 bytes are reserved in memory. That amount of space is reserved in memory for int data types. The next data type is the char data type. Now, the char data type is used to hold characters, and the amount of memory space each char data type corresponds to is just 1 byte. Now, one interesting point to note is that how much memory space would be reserved for a particular data type is fixed for the char data type. That means it's always 1 byte or 8 bits. But for int data type, or for that matter other data types like double or float, which we'll discuss next, the amount of memory space that would be reserved for this data type could be variable. That would depend on the compiler and or the machine, that means the microprocessor or the architecture in which the C program is being executed. Let us now discuss the char data type in more details with the help of another of our programs. So in this program, if you look at this statement, char z semicolon, what it does is that it declares the variable z to be of char data type. So z is a char type variable. Now, how do you initialize this variable, you initialize this. That means you put the value of a character inside Z. So how do you do that? You use this statement. For example, Z is equal to single quote A single quote. That means the character A is put inside the car variable Z. Now, what is this character A? It looks like the character A that we type or find in the keyboard, computer keyboard. Now, for this you need to know that all these characters, alphabetical characters or the numeric characters 1, 2, 3 that you find in the keyboard, along with other characters, they all belong to a set called the ASCII character set. Now, I'll just show you. Yeah, so as you can see, if you go to this site ASCIItable.com, it has a list of all the ASCII characters. Now, ASCII stands for American Standard Code for Information Interchange. So it's a standard which is globally followed and obeyed. Now, the different ASCII characters are listed in this table. As you can see, how many ASCII characters are there? It starts from 0 to, let me see, 127. So maybe I should highlight this for your convenience. So the first ASCII character corresponds to the decimal number 0 over here. See over here, and this actually represents the null character. So each ASCII character basically is a decimal digit, not decimal digit, a decimal number, and it corresponds to an actual character which is listed on the right, and the decimal number is listed to the left. So it starts from 0 and it goes all the way down to 127. So this is the decimal number corresponding to the ASCII character DL or delete. Okay, so this also is an ASCII character. When this statement is executed, then, as I said before, the ASCII value corresponding to the character A, which happens to be 97, gets inside, or rather is put inside, the variable, car variable Z. Now, if you want to print the value of Z, you may use different format specifiers. Now, in this print statement, as you can see, the Z value has been printed twice. The first time we are using the format specifier %C, and the second time we are specifying the format specifier %D. What we would expect is that the first time the character value of Z, which happens to be the character ASCII character A, would be printed over here, and the second time the value of Z is printed, we would expect the ASCII value, the decimal ASCII value, that is 97, would be printed over here. So these two placeholders would result in different values of Z being printed, one being the actual character value and other the actual decimal ASCII value of the car variable Z. Now interestingly, what you can do is, instead of assigning the single character A to the car variable Z, you can directly assign the ASCII value 97 to the car variable Z. And if you use the same printf statement again, you'd find that when you are using the format specifier %c, the character corresponding to this ASCII value, which happens to be A, is printed in the place of this placeholder, and the actual decimal value or the ASCII value 97 is being printed in place of this placeholder. So why not we actually run, execute, and see for ourselves, execute this program and see for ourselves what we expect is what we actually obtain or not. So let's execute it. First we need to compile, so there are no errors, and then we run. So let's see. Okay, so it's taking a little time. Fine. So as you can see, let's shift it over here. Z is equal to A is equal to 97. This corresponds to this printf statement, and here again Z is equal to A is equal to 97. This corresponds to this printf statement. So both are giving identical results. So we are now convinced that you can assign a single character using single quotes to a car variable. Instead, you can also assign the ASCII value, this ASCII decimal value corresponding to the character, to the car variable. Both would mean one and the same thing. When we declare a variable to be of type car, what we do is we let the characters corresponding to decimal codes from -128 to +127 to be stored inside the variable. Why? Because, as I said earlier, that a car data type corresponds to 8 bits or 1 byte of memory, and 2 to the power 8 is 256. So minus 128 to plus 127 constitute 256. On the other hand, if we use the data type for the variable Z to be of unsigned car, then what happens is the size of the data type remains the same, but all the negative decimal digits are removed and only the positive decimal codes from 0 to 255 are allowed. Now let's have a look at the ASCII character table. Let me make it full screen. Yes, as you can see, the decimal codes for the ASCII characters starts from 0 to 127, that is a total of 128, all positive values. So all ASCII characters correspond to positive decimal numbers 0 to 127. But as we just saw a little while earlier, the range of decimal code, the range of decimal coded characters that can be accommodated inside a card data type is either -128 to +127 or from 0 to 255. So we are left with another 128 decimal codes. So the decimal codes which lie outside the range for the ASCII character codes, that is from 0 to 127, those decimal codes correspond to some other characters which we may say belong to an extended ASCII character set, for example Unicode characters, and so on and so forth. Now suppose we assign the decimal code -10 to the car variable z as shown over here. Now note that -10 lies within the range for the card data type, that is -128 to +127. However, this code cannot be called an ASCII code because it is negative, and ASCII codes are always positive from 0 to 127. So if we print the value of z both to obtain its character value as well as its decimal value, let's see what happens. So let's compile and execute it. Well, that's interesting. So if you look over here, maybe I should circle it properly. Over here, the character that is being printed is the division symbol. Now there is no ASCII character for the division symbol, but obviously there is one in the extended ASCII set, if we might call it, or in some other character set, and the value of -10 is printed as it should be. Let's discuss another interesting fact. As earlier mentioned, the range of the card data type is -128 to +127 if it's signed, and for unsigned car it is 0 to 255. Now what if we assign a number which is greater than or beyond this range? Suppose 322, the decimal number 322 is assigned to the car variable. What we would expect is that there should be some sort of an overflow, but let's execute the program and see what values are actually printed for the character and the decimal number. If at all any character will be printed, or it would result in an error, we don't know at this point. So let's execute it and see for ourselves. Okay, so this is the result in the output window, and this is the message window. So let's use the highlighter pen, and as you can see in the message window we have a warning that an overflow has occurred, as we had expected, because the value 322, the decimal number 322, is beyond the range of the data type card. Now yet we find that we have some result. The value that was put inside Z is the decimal number 322, but here we see it is 66, and for the character value we see it's B. Interestingly, if you again have a look at the ASCII table, okay, so here you see the decimal value or the decimal code 66, which is an ASCII code, indeed corresponds to the ASCII character B. So what's happening here? How could we obtain the decimal value 66 printed over here and the corresponding ASCII character B printed over here, while we assigned the decimal value 322 inside the card type variable Z? What happens is the lower order 8 bits or 1 byte, these 8 bits are retained and the higher ordered remaining bits are discarded. So if we calculate the value of the lower ordered 8 bits corresponding to 322, we'd find that value corresponds to the decimal number 66, and which again, as I just showed you, corresponds to the ASCII code or the ASCII character B. So I hope you have understood an interesting feature which has to do with card type data type variable. Okay, so apart from the int and char data types, we also have data types which deal with real numbers, real decimal numbers, like say 22.53, 30.65, and so on and so forth. Now, the two basic data types for real numbers are float and double. Float is called single precision and double is for double precision. When we declare a variable of type float while executing, the memory space that is reserved is 32 bits or 4 bytes. And when we declare a variable of type double, on execution, the memory space reserved is 64 bits. That corresponds to 8 bytes. When we talk of single precision for a float variable or float data type, we actually mean 6 digits of precision. And when we talk of double precision, what we actually mean is 15 digits of precision. That means for float, after the decimal point, we have 6 digits of precision, and for double, after the decimal point, we have 15 digits of precision that is used internally. Also, the range for a float data type or double data type, which we said is 32 bits and 64 bits respectively, may differ from compiler to compiler or from machine to machine. If you remember, I had touched upon this keyword unsigned. Now, unsigned is a data type modifier because it's modifying the range, some property, a range of the card data type variable. Now, there could be other data type modifiers like long and short. Now, why would we need them? For example, we would be dealing with integer values residing in a very short range, very small integer values. So we may as well conserve memory by using the short data type modifier in front of int. So instead of writing int, we write short int. It may also be possible, in fact it is possible, to just discard the int and write short. Short would signify short int. Also, if you want to extend the range, we could use long int or simply long. If you want to increase the range of the integer data type. Similarly, we could also have long double, which is though very rare, but you could have it to store double values of very high precision. Some compilers may allow you to do that. One thing I forgot to mention earlier is that when you use decimal numbers or decimal constants or literals, whatever you call them, in the form as I'm showing over here, say 3.1415926, this would represent a double constant or a number corresponding to a double data type. But if you append this with f, then this number 3.1415926f would now represent a float data type literal. So we have discussed the 4 basic data types: int, char, float and double. Keep in mind that these are keywords, and these words cannot be used as names of variables or functions or any identifier. Now I hope that you have had some understanding of the data types, basic data types. I would ask you to go through the tutorials in more detail to have a better understanding. Of course, you can contact me through your Google Classroom as and when required.